Hello, this is a video about power function families. This explains some of the material that's needed to do the homework that's assigned on Monday, December 2nd, which is page 12, numbers 3 and 4. The power function family. The functions describing dependence of a light circle area and light intensity on distance are only two of many direct and inverse variation patterns that can be modeled by rules in the form y equals k times x to the r and y equals k over x to the r. We did the direct variation of the light circle area. As the distance increased, the circle got bigger, and that was related to the square of the radius, as area is, and the light intensity. As the distance increased, the light got dimmer, and that was also related to the radius of the circle. As the circle got bigger, because the distance got bigger, the light got dimmer, and that is an inverse variation, and it was a power function because it was the radius raised to the second power. Use your calculator or a computer graphing tool, like this picture right here, to explore the relationship between the power r, so r is the power in each of these functions, the number that it is raised to, and the constant of proportionality k. K is the constant that is in the function. We're going to keep k equal to 1 for simplicity's sake at first, and then after we explore what happens when you change the exponent, then we're going to change some values of k. To get a good picture of the graph, be sure to set your graphing window so you can see both positive and negative values of x and y. In this graph, it's a little bit blurry, but this goes from -5 to +5 on the x-axis and from -5 to +5 on the y-axis. Those are good settings for your calculator. As long as you can see both the positive values of x, the negative values of x, and the same for the positive values of y and the negative values of y, you should be okay. You can usually use the pinching motion on your iPad calculator to zoom in or out. So we're going to be using an app called Desmos, which you should already have downloaded. That app is a good graphing calculator. Equivalently, you can use your TI-83 or 84 if you own one. You can use the TI Inspire app on the iPad, or if you don't have any of those, which you should have at least one of those things, you can use the GraphCalc HD app that already came loaded on your iPad. The Desmos calculator looks something like this. Here's the viewing window with the positive and negative values. Here's where we're going to enter functions. Over here, you can do all kinds of fancy things with this calculator. We're going to start with some basics though. So, problem number 3 on page 12. How is the shape of the graph for a direct variation function? All direct variation functions can be written in this form. How is that related to the values of r, which is the exponent, and k, which is the constant of proportionality? Like I said at first, we're going to keep k equal to 1 at the beginning, and then we'll change it later. To see patterns that help answer this question, you might begin by studying examples in which we keep k equal to 1, but r changes from 1 to 2 to 3, etc. Then explore what happens for different positive and negative values of the proportionality constant k. Describe the patterns you observe. You're not only going to describe them, you are going to draw what you see, a worksheet. You should have a worksheet that looks like this. It's available on iTunes U under today's date. The directions right here are similar to what we just read on page 12, problem number 3, and there's room to draw in the graphs that you see. So starting with the simple. Here, notice we've got k equal to 1. That's the 1 times out front. Technically, you don't even need that, but I wanted to be explicit with this to see that it fits the pattern of k times x to the r, and in this case, r equals 1. That, of course, can just be rewritten as y equals x, which, of course, is just this straight line. So that one's pretty easy and straightforward. That simplifies just to y equals x, which would have the points 0, 0, 1, 1, 2, 2, 5, 5, etc. When you make one little change, though, it changes the graph significantly. Notice that now r equals 2. We've kept k equal to 1, but now r, the exponent, has raised to 2, and that gives us y equals x squared, which is the familiar parabola right here. Please notice that we said that with direct variation, when x increases, y also increases. That was a simplification for the early variation patterns that we're looking at. That is only true when you have from x equals 0 up in the positives. You can see here that the value of y is decreasing until we get to this point, the vertex, and then it's increasing. That is an example of direct variation because it fits this pattern right here. We're concentrating on the pattern of the equation and what that looks like, what the graph of this power function looks like. Number 4, how is the shape of the graph for an inverse variation function? This is what inverse always looks like. Notice that x raised to the r is on the bottom of the fraction. We're going to do the same thing. We're going to start by increasing the exponent, the value of r, from 1 to 2 on up. Again, using the Desmos calculator, or whichever calculator app you're using, you should get graphs that look similar. Please notice that this is 1 over x. I've got it written as 1 over x raised to the first power to be explicit, so that to show that it fits the format. But x to the 1, of course, is just x. So this is the graph of 1 over x. And it goes way up here as we get close to 0. And as we approach 0 from the negatives, it goes way down here. But this graph never actually touches 0 here along the y-axis. Hard to see that on this graph, though, but take my word for it, that's a discontinuity. This graph also has a discontinuity along the x-axis. There's no way to make this function equal to a y value of 0. Anyway, this is the characteristic shape of this kind of graph. It goes like this, which we saw when we were doing the on a roll experiment. This looked like the height versus time graph, but there's a mirror image of it over here in the negatives. This graph is symmetric to the positive values of x. It's just that now we have the same values of y, they're just negative values of y. If you turn this graph kind of on its corner a little bit, this kind of looks like the wings of a butterfly. That is a terrible picture, sorry. But you get the idea. As we change 1 over x squared, now the value of r is 2, so we've got 1 over x to the r, where r is 2, or 1 over x squared. We notice that we have a similar looking graph, except in the negative values of x, we now get positive values of y. This graph looks kind of like a volcano to me. We are looking for characteristics of the power function when it looks like this, 1 over x squared. Your job now is to finish page 12, problem numbers 3 and 4, using higher values of r. I did values of r that are 1 and 2. You do 3, 4, 5, and 6 using your own graphing calculator or graphing calculator app, and write the answers in on the worksheet. And then you can explore what changing values of k into higher positive numbers and negative numbers does, instead of just leaving k equals 1, and describe the pattern of change there. So finish page 12, numbers 3 and 4 for class on Wednesday, December 4th. Done.